Hi, I am Alexandra May Hoya from ECE31 of De La Salle University Dasmariñas, and I'm going to do experiment 2 of our power electronics laboratory subject entitled Instantaneous Power, Energy, and Average Power using PSpice.
Power Electronics Experiment 2 Instantaneous Power, Energy, and Average Power using PSpice. The objectives are to simulate power electronic circuit to determine the voltages, currents, and power quantities, and to utilize the functions to measure the energy and steady state RMS current. For the procedures of the experiment, Part 1, Voltage controlled switch in PSpice. The first step is to open ORCAD Capture PSpice and click New Project. To do that, click Start, type ORCAD, and click ORCAD Application. And then click on New Project. Step 2, choose the analog or mixed AD and name it as Experiment 1. Analog or mixed AD is selected, Experiment 1, and then the next step is to create the circuit as shown below. To do the circuit, click Place, PSpice Component, Source, Voltage Sources, and Sign. Place the source and click Place again, PSpice Component, PSpice Ground. Just copy the circuit, add the resistor, and wire. The next step is to change the values according to the shown figure 4. Frequency 60 and AC should be set to 0 and resistance is 5. The next step is to select the time domain transient in the simulation setup. Enter a runtime of 16.67 milliseconds for one period of the source. To do this, click this icon, New Simulation, and put a name. In my case, I put Trial 1 and click Create. And then after that, you see a pop-up menu and change the runtime to 0.01667 seconds. That is 16.67 milliseconds. Click Apply and then OK. And then click Run. This will appear, and then to add the traces to see the waveforms, click Trace and then select WR1, VV1 plus, and you'll see this waveform. The green waveform is the waveform for the instantaneous power, and the red is for the sine wave of the voltage input. Now that we have the instantaneous and the sine wave waveforms, we can now add the current in the resistor. To do that, add trace, and select IR1. Click OK. And as you can see, the waveform started at its negative cycle, and to change this to its positive cycle, all you have to do is click this and put a negative sign here and click OK. And as you can see, it has already changed. The next step is to add another trace, the average, and to do that, type AVG parenthesis W, another parenthesis of the R1. This is the formula to be used to get the power average of the instantaneous power in one or more cycles. After typing the formula, click OK. This yellow waveform is the average power of the instantaneous power. Right-click cursor on to check the waveforms and click on that green button near WR1, and as you can see, you can navigate to the waveforms, and this box at the lower right is the table for the values. And as you can see, as I change the or navigate through the cursor, the values at the bottom right changes, and As you can see, the value of the power here is 19.98, the voltage is 9.997, and the current is 1.994. And as I change onto the yellow waveform, you can see that the average power has 10.07 watts. We can compare the experimental data using the circuit values in the experiment. As you can observe, the theoretical values has an input voltage of 10 volts and a resistance of 5 ohms. Using the Ohm's law, where current is equal to V over R, if we are to substitute the values, 10 volts over 5 ohms is 2 amps. And in the experimental value, as observed in this picture from the simulation, the current in R1 is 1.9994, which is very close to the theoretical value. It can also be observed that the theoretical value for the instantaneous power, where the formula is P is equal to voltage times the current, the given voltage in the circuit is 10 volts and the computed current is 2 amps. That will give us 20 watts in power for R1. And as observed in the experimental values for the instantaneous power, the value for WR1, or the power in R1, is 19.988 watts, which is close to the theoretical value of 20 watts. For the part 2, the RMS, the first step is to create another project, but this time using the circuit shown below. We will copy this circuit. So just like the previous part of the experiment, you have to create a new project, name it, click OK, create this as a blank project, and then in this page we will copy this circuit. So let's do it. So first, place source, voltage source, and a pulse voltage source, and then place another resistor here and place another inductor here. Rotate it. Okay, and then we are to wire the circuit in series. After wiring, of course, we need to place the PSpice ground. And of course, change the values of the components. The resistor is 2 ohms, the inductor is 10 millihenries, and the voltage pulse has a V1 of 0, a V2 of 20, a TD of 0, TR of 1N, TF of 1N, PW of 8M, and PR is 20M. And then we should create new simulation and then type any name that you want, and then the pop-up simulation settings, change the runtime to 0.1 seconds, apply, and then click OK. And then run the simulation and click here, and then we have to add the trace, and just like before, add trace, and we're going to select the current in R1, and as you can see, it is inverted, so we have to add the negative sign in the trace expression, add another trace, and this time we are to get the RMS of the current in R1. So type RMS parenthesis I parenthesis R1 close parenthesis, and this red waveform here is the steady state current, and as you can see, this green waveform here is the current in R1, and the red waveform is the steady state current. So if we were to observe the waveforms, we could see that if we are to add another trace, we're going to add the current in the inductor. As you can see, the blue waveform just overlapped with the green waveform. This means that they have the exact same current. So this only means that the current that passes through both the resistor and the inductor are the same because they are in series. So as you can observe, we can say that in an RL circuit, the current that passes through our resistor and the inductor are just the same. The expected outcome of the experiment was seen in the simulation. This is because, as we can observe, the RMS current has a value of 4.68, which is at the end of the cycle in specific transient time. And if we are to observe the expected output, the RMS current also has the value of 4.6389, which is very close to the experimental value that we got in our experiment. So that's all, and thank you. God bless.
Conclusion. From the first part of the experiment, it was observed that the instantaneous power is the power of a circuit in an instant. From the relationship of the waveforms in the first part of the experiment, it was also observed that the average power is the power average over a second or a given number of cycles in the simulation. For the second part of the experiment, it was observed that as we apply the square wave pulse signal, the resulting voltage showed the same current waveform for the resistor and the inductor. In conclusion, the effect of an RL circuit is the voltage across the inductor, which increases with time, and the current that rises to their final value exponentially. The current and resistor waveform will have the same values, since from the Ohm's law formula, the current and the voltage are related with V equals IR. This means that in the circuit, the same value of current will pass through the resistor and the inductor. Recommendations. It is recommended to have a background knowledge on how ORCAD functions work and how to produce and interpret the data gathered.